All right, everyone. So welcome. We are now in the 18th lecture. We're on the end of week 9, which is we're 60% of the way done with the semester. And we were working on confidence intervals and hypothesis testing. And we did the basics of confidence intervals. We did the basics of hypothesis testing. We did chapter 18 on inferences, all stuff that's going to be on the exam. And let me actually load up. Let me load up the syllabus for this class so I can make sure that I do the right chapter next. So we're in week 9 now, according to this, in week 9. Most people are taking the test today, but we're a little bit behind. Actually, let's see, 17, 18, and they've started chapter 20. So let's jump ahead to chapter 20. And we're actually not that far behind anymore, so that's nice. Okay, so chapter 20. Okay. So chapter 20, okay, we don't need to do that. Okay, so how do I turn off? Hold on, it's making too much noise. I am recording, but I don't know how to turn the sound off. Oops, that's not what I want. I don't know how to turn sound off on this thing. So hopefully that works. Okay. So bottom left, you can change status to do not disturb. In settings, you mean? Is that what you mean in settings? That's okay. I think I did it. Okay. That's okay. I think I did it. Let's get started. Okay. So up until now, we have been discussing confidence intervals and hypothesis testing about what have we been working with so far in this class? For a mean, we know that the confidence interval is x bar plus or minus what? Someone remind me, x bar plus or minus what?
Z star sigma over square root of n.
Okay. And if we have a hypothesis test, basically we have a null hypothesis that the mean has some value. And then we had the alternative hypothesis, either HA or H1. And we had 3 options, either greater than, less than, or straight up not equal to that value. Right? Those are the things that we've done so far. And essentially what's going to happen is we're going to use our sample mean x bar. We're going to use sigma. We're going to use n. And we're going to use the confidence level. All of these are used, of course, both in the confidence interval, and they're also used in the hypothesis testing. And in the case of the hypothesis testing, we calculate our p-value, calculate the p-value, and then we compare the p-value to what? What do we compare the p-value to come up with whatever conclusion we're going to make? Oh, someone's texted something. Let's see what they say. So usually 0.05. Doesn't have to be 0.05, but in general, we compare it to alpha, the significance level. We compare it to alpha, the significance level. And usually we take 0.05, but we don't have to. Just be aware of that, right? Depending on the problem, it might not be the 0.05. I would certainly recommend on your notes for the test to have your Z stars for 90%, 95%, 99%, because they're used quite often. Okay, so this is what we've done so far. But what happens, for example, if you don't have sigma? Is there nothing that you can do? Well, no, there is something you can do. You have to approximate sigma. And when it comes time to approximate sigma, we have to account for that. Because now that we're approximating something, our knowledge of the problem is a little bit less. So for a given confidence, do we expect the confidence interval to get wider or smaller due to the fact that we have a little more uncertainty in the problem than we did before? All right, we have a certain amount of confidence that the mean is between this number and this number. Well, if there's some more uncertainty in the problem, do we have to widen those numbers to make our confidence interval wider? Or do we have to bring them in? So someone typed and said the interval gets wider. That's 100% correct. Because of the uncertainty, the confidence interval gets wider. And we take that into account by changing Z star to T star. We're going to use the T distribution for that. Our T star values are a little bit bigger than our Z star values, so the confidence interval gets wider. And rather than using sigma, which is the population standard deviation, we're going to approximate sigma by using what? What's something that we can use to approximate the population standard deviation? What do you think is a good thing that we can use to approximate the population standard deviation? Excellent. The sample standard deviation. So we'll see that in a minute. Okay, so excellent, excellent, excellent. So in general, whether we use the Z star or the T star, we are still working under the assumption that it's a simple random sample that has not changed, and it comes from a normal distribution. It's just that now we also do not know sigma. So we have a little bit of uncertainty that we didn't have before. Because of that, rather than using sigma over the square root of n, we're going to use S over the square root of n, where S is the sample standard deviation, which requires an extra computation, or on crunch it's an extra computation, but somewhere along the line, an extra computation is required. Rather than saying, here's sigma, plug it into the problem, we say, we don't know sigma, but we will approximate it with S. The rest of it, so far, in terms of the margin of error, is the same. But again, we're not going to use Z star. We're going to use T star. So let's talk a little bit about the T distribution instead of the Z distribution. We know from before that Z, our Z score, is equal to X bar, that's our sample mean, minus mu, that's the population mean, divided by the standard error, or the standard deviation of the sample distribution, which is sigma over the square root of n. So now we change Z to T. And the change is manifested in the fact that we are not going to be using sigma, we are going to be using S instead. And it has this extra weird thing called the number of degrees of freedom. Z did not have this degrees of freedom concept, but T does. Okay, because even though we're using T instead of Z, we do expect that as the sample size gets larger, we are getting closer and closer and closer to a Z. Okay, if the sample size is really large, then the difference between T and Z is not so big. So every time you use T it always comes with a number of degrees of freedom. In this case, where we're basically doing the same thing as we did before, but just don't know sigma, the number of degrees of freedom is n-1, and I will show you how that manifests itself in terms of calculations in a second. Okay, so here is the difference between a z and a t. They look very, very similar, and you might even say, well, they're both bell curves. A bell curve is descriptive. If it's a true bell curve, if it's a true z distribution, it has a very specific shape in terms of where it curves and how much it curves, and all the details along the line are very, very specific. For t, while it looks like a bell curve, it's not quite a bell curve. It's a little bit lower, doesn't go as high, and it compensates for being a little bit wider. If you look at these things, the solid bar is the normal, which is the z. And then notice how with 2 degrees of freedom, it's this thing here, it's dropped significantly. So it's lower, but on the outside, it gets wider. When I go to 9 degrees of freedom, it's not quite as low, but it still is a little bit wider, but again, not quite as wide. So as the number of degrees of freedom goes up, it gets taller, it gets skinnier, and it gets closer and closer to a z. And when we look at the table, we're going to see that when a number of degrees of freedom is really big, the difference between t and z is exceptionally small. But looks-wise, they look very similar. Okay, so let's do the 1 sample t confidence interval, much like we've done the 1 sample z confidence interval. When you look at the formula, it's pretty much exactly the same. It's just we don't use z star, we use t star, and we don't use sigma, we use s. Okay, but let's do an example that shows that it's, I'll give you a second just to write it, but let's do an example that shows that essentially it's exactly the same thing. So we have a study at tipping at restaurants. We did this example in the past, but in the example in the past, we actually use sigma. In fact, let's compare the two. When I look at example 16.3 here, we have the same 10 numbers, but what we see here is that they give us that sigma is equal to 2. So when I go to crunch it for that example, and here's all the data, and I say compute a confidence interval. First of all, if you know sigma, you're going to use z. It's 1 sample. So I click it. I go to confidence interval. I say, let's say 95%. I say sigma is 2 because they gave it to me. And the sample is the percent column. And I calculate, and there's my confidence interval, which they're not letting me move for whatever reason. Okay, I don't know how to move. Okay, that's not, I don't know how to move it. Okay, but hopefully it won't get in the way of the next one. So how do we stop sharing for a second, see if I can figure this out. Why is it not letting me scroll? Okay, I'm gonna close this down and open it again. So let's share screen again and try this again. So I gotta crunch it and I go to statistics again, Z, 1 sample, confidence interval, sigma is 2, sample percent, and I have my answer, which now it's letting me move. Okay, so get out of the way. That's the confidence interval for Z. But if I do T, and I do the 1 sample T confidence interval, 95%, Notice that there's no entry for what? What did they not ask me for that they did ask me for the Z?
Standard deviation and mean.
Well, they don't ask me for the mean. They didn't ask me for the mean before, but they did ask me for the standard deviation. So why don't they ask it for me here? Because I don't know it, right? I don't know it. But if I calculate, what do I notice about the confidence interval now compared to the one before?
It's bigger.
It's a little bit wider. Not much, but I go a little bit left, a little bit right. The confidence interval is a little bit wider. Do we agree with that?
Yes.
The left side got smaller. The right side got bigger. The confidence interval got wider. That is the effect. Notice what they give me. The mean hasn't changed, of course. I don't have the deviation, so they don't give it to me in this case. How many degrees of freedom do I have? One less, excuse me, one less than the sample size. And they also throw in the standard error. The standard error, just so you have it, this is S over the square root of n. So you can reverse engineer the standard deviation by saying 0.4388 equals S over the square root of 20, and therefore S equals 0.4388 times the square root of 20. So you can reverse engineer S, but they don't actually give it to you. Okay. Other than that, there's really no difference between what we did before and what we do now. Okay, Crunch it's going to do it all for you anyway. So the difference is when you go to Crunch it, don't pick Z, pick T, and do exactly the same thing. Okay, are there any questions on that?
Can we see an example?
We just did an example. why
Oh,
didn't
that was
you like,
it?
yeah, why didn't you like the example that I just did?
Oh, I meant like looking at a problem, like for example, the homework.
No, right here. We just did it.
Wow.
Here's all your data points. We calculated the T interval. That's it. There's not going to be any other questions. Right? It's the same thing. Everyone's the same thing. I mean, every one of these types of problems is the same thing. Okay? Yes, no, maybe so? Yes?
Yes.
So now let's go to the one sample T test. All right, what about hypothesis testing? How does that affect it? Well, the answer is we do exactly the same thing. We're still testing a null hypothesis of mu having some value that has not changed. And we're still comparing it to the alternative where either mu is greater than, less than, or not equal to some value. Okay, that part is exactly the same as it was before. So, you okay? Okay, so what is different than before is the fact that we are now dealing with a situation where we do not know sigma. That is the only difference. We don't know sigma. So as such, the cutoff point, the point that we get for which we're going to compute our p-values, is not going to be z, which is x bar minus mu naught over sigma over the square root of n. I can't use it because I don't know sigma. It's going to be x bar minus mu naught over s over the square root of n. Because of that, it's going to be a little bit different point than it was before because we get a different value. And as such, the p-value is going to be a little different. okay, the p-values are going to be a little different. How does that affect you in terms of what you do? It doesn't affect you in the slightest. Not in the slightest, because at the end of the day, you're going to do exactly the same thing. You're going to go to crunch it, and you're going to, well, we'll do an example in a second, but you're going to go here, you're going to go to T instead of Z to one sample, because we haven't learned anything else, and you're going to go to hypothesis test, and you're going to pick whether it's one-sided or two-sided, et cetera, et cetera. You're going to do exactly the same thing. The only difference is we don't know sigma, so we use T instead of Z. So let's do an example that illustrates that. What do you do when you don't know Z? So here we have an example. Okay. To investigate water quality in late July 2016, the Ohio Department of Health collected vials of water from 12 beaches on Lake Erie in Cuyahoga County. Those vials were tested for that's the stuff I'm eating right now. Those vials were tested for some crap, and an unsafe level of crap literally means there's a higher chance that disease-causing bacteria are present and more risk that a swimmer will become ill if he or she should accidentally ingest some of the water. One website considers it unsafe if a 100 milliliter vial of water contains more than 88 coliform bacteria. So essentially, we're testing whether or not it's more than 88, right? Of course, versus what? Versus being 88. So the null hypothesis is that the mean is 88, and the alternative hypothesis is that the mean is greater than 88. And the question is, do we infer from our data that the mean is greater than 88, and therefore we're going to reject the null hypothesis? Or do we infer from the data that the mean is not necessarily greater than 88, and therefore we can't reject the null hypothesis? Notice I say nothing about accepting the null hypothesis. It's all about, do I reject it or do I not reject it? Okay, so we went out and took a sample of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the question is, are these data good evidence that on average, the levels of crap in the beaches was unsafe? So let's go to crunch it. Let's close down this crunch it, I don't need it. And we have crunch it here. So here is all my data. Notice that's all I have. I have my data. So I go to statistics. I go to, is it going to be Z or T?
T.
Yeah.
Leaving.
You're leaving?
Yeah.
You're done?
No, for today.
What time are you back tomorrow? 9 a.m.?
8:30.
8:30? Okay.
Yeah.
Excellent.
Okay. It's not right.
So I can't walk?
Yeah, you can walk, but we leave the fan on and you put it on around 1 hour.
1 hour?
Yeah.
1 hour. It's 4:55, 6 o'clock.
Yes. But you can walk.
I can walk.
Yeah.
Process, amigo. Thank you so much. All right, I'll see you tomorrow.
Yeah.
Okay. Okay, sorry about that, guys. I sincerely apologize. So let's, where I totally forgot where I was. Oh yeah, okay. So are we using a Z or are we using a T here?
T.
T, I mean, for two reasons. One, we're in the T chapter, so it's kind of like a pretty good giveaway. And also, we don't know sigma. So we go to T. Is it one sample, two sample, or something we haven't learned yet, which is a paired sample? It's one sample. Are we doing a hypothesis test or are we doing a confidence interval? Hypothesis test. What is the mean under the assumption of the null hypothesis? Is it two set? Okay. That was pretty quick. And this column is that. So we calculate null hypothesis, the mean is 88. Alternative, what we're testing against. The mean is greater than 88. We have 12 in our sample. That's our sample mean, sample error, 11 degrees of freedom. Our t statistic is 0.9499, but more importantly, the p-value is 0.1813. What does that tell us? What does that p-value tell us? This is the whole point. Okay, if you can't come to a conclusion based upon your test, why do the test? So what is the conclusion of the test? The water is unsafe. Well, let's take a step back. Are we concluding that we are rejecting the null hypothesis or not?
Not reject.
Not reject, because the p-value is 18%. Usually 5% is the cutoff if we're not given another value. So the p-value is greater than 5%, correct? If the p-value is greater than 5%, or alpha in general, do we reject or not reject? What is our conclusion? We do not reject the null hypothesis. The value that we got is not crazy rare enough for us to question the null hypothesis. As such, we do not reject the null hypothesis, which means that we cannot conclude the water is unsafe. Okay, is it safe? I don't know, but we cannot conclude that it's unsafe. Agreed? Does that make sense? I mean, the whole process, it's, once you kind of get the hang of doing these hypothesis tests and confidence intervals, especially on Crunchit, it is extremely straightforward. Okay, it's all, the next few chapters are just going to be different situations and different types of problems, but they all have the same basic the same basic process, right? So Jamar, you say kind of, which parts? Okay, kind of means that there's something you don't understand. If I can address it, I'd love to, but I need a little more specifics.
So I'm just like the whole overview of T is just if you're missing
Sigma.
sigma, that's what T is for.
Yep. Use Z if you know it. Use T if you don't.
All right.
Other than that, the procedure is exactly the same.
Okay, thank you.
Okay. I mean, all these different examples and whatnot, but that's what it comes down to. Okay. So then we go to the match pair t-test. Okay. The match pair t-test, remember on Crunchit, it said one sample, two sample, or pairs, or paired. That's what this is. This is the paired. And the paired is when you are comparing two things that are connected. If I'm interested in whether or not men or women are different heights, and I just pick 10 random men and 10 random women, there's no connection between them, right? They're completely independent of each other. But if I do like a before and after test, or I check something of yours, like how proficient are you at typing, how many words per minute, and then I have you take a course, and then I give you an after test of how many words you can type per minute, there's a connection between the before and the after. It's not 10 random people before and 10 random people after. It's the same people before and after. It's matched. Okay, the pairs are matched up. When that happens, a before and after, a left hand versus right hand, left eye versus right eye, when you have a matched situation, then we use the matched pair t-test. As you're going to see, the matched pair t-test is pretty straightforward. One second. Okay, so let's look at this example. Do chimpanzees collaborate? So humans often collaborate to solve problems, and the question is, will chimpanzees recruit another chimp when solving a problem that requires collaboration? Researchers presented chimpanzee subjects with food outside their cage that they can bring within reach by pulling two ropes, one attached to either side of the food tray. If the chimp pulled only one rope, the rope came loose and the food was lost. Another chimp was available to partner, but only if the subject unlocked a door joining the two cages. The same 8 chimpanzee subjects faced this problem in 2 versions. The 2 ropes were close enough together that one chimp could pull both, no collaboration needed. Or the 2 ropes were too far apart for one chimp to pull both, collaboration needed. Okay. Table 21.4 shows how often in 24 trials for each version, each subject opened the door to recruit another chimp as a partner. Is there evidence that chimpanzees recruit partners more often when a problem requires collaboration? So tell me, what in this problem tells you that this is a matched pair t-test? Not exactly. There's more to it than just 2 different versions. There's something very specific. What makes this a matched pair t-test versus what we're going to learn later, which is a 2-sample t-test? What is it in the question? Read it. Dad? Yeah. Don't turn off the fans for another hour, okay? What? Don't turn off the fans for another hour. Don't do. I'm sorry. Don't what? Don't turn off the fans for another hour. Oh, I'm not turning anything. Yeah, he said he's gonna keep them on for another hour. Would I keep them off? Yeah, just be careful, but don't turn them off for another hour. Okay. Okay. So this is not a before and after. Okay, this is not a before and after scenario. Read it again. Anyone? I mean, I guess it's before. I mean, obviously, it is a before and after in the sense that one of them had to go first. But yes, it's the same chimpanzees faced this problem in 2 different versions. It wasn't 8 chimpanzees for this way and a different 8 chimpanzees for this way. It was the same 8 chimpanzees for both. The same 8 for both. Okay, that's what makes it a matched pair t-test. And when you have a matched pair t-test, what you're interested in is not the actual number for the first case and the actual number for the second case. What we care about is the difference. 16 minus 0, 16 minus 1, 23 minus 5, 19. It's the difference that we care about. And once you have the differences, once you have this column here, then it's a regular t-test. So let's go to crunch it. It has collaboration and non-collaboration. We go to statistics, we go to T, we go to paired. Okay, what type of problem are we doing here? It's a hypothesis test. What is the hypothesis test here? What are we testing? What are we testing here? Right, but I'm saying mathematically. I mean, we gotta fill this in, right? So mathematically, what are we testing is the question. We know it's a hypothesis test. What's the mean difference under the null hypothesis? We're testing to see if there's a difference, right? So if there's no difference, it will be 0, right? Is it a greater than, less than, or is it a one-sided situation? Anyone? We're seeing if there's a difference, right? But I guess technically, we're seeing is there evidence that chimpanzees recruit partners more often when a problem requires collaboration? So we're checking whether or not collaboration is greater. So yes, it is a greater than. The first variable is the collaboration variable. The second one is a non-collaboration variable. And then we calculate. And what do we see in this situation?
That it's true.
Now, what's true?
The null hypothesis is true, so we do not reject.
What is our p-value? I guess is better to say. What's our p-value? Right, it always comes down to the p-value, doesn't it?
A tenth of a percent.
It's so small. It's so small that we are going to reject the null hypothesis. And therefore, yes, there is evidence to suggest the fact that when collaboration is required, they collaborate. So these are one of the things that, you know, sociologists or zoologists or whoever ologists use to determine how smart an animal might be. Right? Do you see, do you see other animals making similar, collaboration efforts? No, right? Less than alpha, rejecting null hypothesis, excellent. Does that make sense? I hope it makes sense. It's once you understand confidence interval and hypothesis testing, again, these things go very quick. Okay. So the only other thing in this section that I want to speak about is the robustness of t-tests. Okay. So what exactly is robustness? A confidence interval or a hypothesis test is called robust if the confidence level or p-value does not change very much when the conditions for the use of the procedure are violated. 1 second. That's right. This is very much the same thing as Z, right? You're basically, it's basically exactly the same thing. Just you don't know sigma. So we use T's instead of Z's. Like a median. Oh, okay. So you're talking about what's called a resistive measure. All right. The median's a resistive measure because it resists changes. It resists changes in value when outliers. This is more about an entire test. So confidence intervals, which are used to test whether or not the mean is a certain value or it's in a certain range, or hypothesis tests is a little more different than an actual measure like a median or a mean or something like that. Okay. So hypothesis tests and confidence intervals are robust if the confidence level or p-value does not change very much when the conditions for the use of the procedure are violated. In other words, if it's not really normal or it's not really an SRS, am I allowed to use it? Well, if you follow the rules, the answer is no. It's got to be an SRS and it's got to come from a normal. Those are the rules. But if it's a robust procedure, then we can get away with it. Okay. So using the T procedures, except in the case of small samples, the condition that the data comes from an SRS is more important than being normal. Okay. And they give us a few things. If the sample size is less than 10, then you can use these tests if it appears to be normal. If it's clearly skewed or if there are outliers, don't use it. If the sample size is at least 15, you can use it. Again, not if there's outliers or strong skewness. Now, once the sample is greater than 40, we don't even care if it's skewed. These procedures are so robust that even if it's clearly skewed, you can still use it if n is greater than or equal to 40. Just don't use it if there's outliers. Outliers are bad. Outliers, we never want to use it with outliers. But even if it's clearly skewed, you can use it if n is greater than or equal to 40. Okay? Robustness is a conceptual idea. It is not a mathematical idea. Okay, so you don't have to worry about doing any math with robustness. But these rules here, if n equals 40, yeah, you still can't use it if there's outliers. Okay, outliers are bad. Do not use it if there are outliers. Okay, outliers are bad. But in practice, you're not going to be given a problem where you can't do anything because they're not going to be able to test you on your ability to do these things. Okay, just remember, if it's normal, then if it's less than 15, not a problem. As long as it's, pretty normal, we're okay. But if it's not normal, but it's skewed, then it's got to be at least 15. But if it's really skewed, then make sure n is at least 40. I showed you that applet, correct? Did I show you that applet one time? We saw already by 5 things that were skewed were already looking normal, right? And we saw by 30 things that were clearly skewed were still about normal. Agreed? But to be safe, go for 40. Okay, to be safe, wait for n to be greater than or equal to 40. If n is greater than or equal to 40, then you can use it. If n is not greater than or equal to 40, then be careful. Make sure. How do you check, by the way, if the data is skewed or not? How do you check? If I give you data, how do you just look at it and say, oh, yeah, that's skewed or that's not skewed? How do you check? What do you do? What do you do in that case? The answer, graph it. Or the 5-number summary. That's good too. Very nice. Yeah, the 5-number summary. 5-number summary is a great way to see if it's skewed, right? If the box is, longer on one side than the other or a longer tail, we got skewness. And that's it. I don't want to go past chapter 20 because you have a test coming up. So I'm going to stay here for questions if there are any. I'm going to stop sharing. But I thought today was pretty good. I mean, we started a half an hour late because we were talking about very important stuff like how awesome I am and things like that. And then in 40 minutes, we basically did an entire chapter. It's as you're going to see, it's very, very straightforward, this stuff. Once you understand it, we should start every class like that. That's right. Thank you, Carly. Your words before, I didn't forget them. I appreciate that. But yeah, if there's no questions, then we're done. So thank you guys. Have a wonderful. Is stats really math? Yeah, stats is really math. Thank you guys. I appreciate it. Have a wonderful day. I'll stay here for questions. I'll stick around. gonna have dinner, but
Thank you.
you're welcome.
Enjoy your birthday, Professor.
Thank you guys. I'll see you guys when I'm older. Bye there.
All right, have a nice weekend.
Jamar, have a great happy birthday.
Thank you.
Vanessa, that's every day. Oh, I think oh yeah, don't forget.